Okay, chapter 7. What are we going to talk about? Solutions, even though you can't see it because the recording button's in the way. Let me move that over here. So far this year we've focused on pure substances, either elements, ionic and covalent compounds. But most of the things we come in contact with every day aren't pure substances, they're mixtures. A mixture is two or more pure substances mixed together. Two types of mixtures. Heterogeneous does not have a uniform composition throughout the sample. And homogeneous, or homogeneous, depending on where you come from, has a uniform composition. So, sweet tea, dissolved sugar in the tea, is that homogeneous or heterogeneous? Homogeneous, yeah. The tea tastes the same whether it's at the top of the pitcher or by the time you get to the bottom of the pitcher. It's uniform throughout. What about air? Nitrogen, oxygen, carbon dioxide, and water. Is it homogeneous or heterogeneous? Is it heterogeneous? So I got 28% oxygen here. I walk over here, now I'm down to 2% oxygen, and I fall over and die? Yeah. No, it better be homogeneous.
It all breaks down.
It's all evenly blended. What about chocolate chip cookies, my favorite? That's heterogeneous. Because there's not the same number of chocolate chips in each cookie, despite what those little creepy elves tell you, okay? What about milk that you buy in the store? Heterogeneous or homogeneous? Yeah, because what's it say on the carton? Homogenized. Yeah, that means it's blended. Orange juice. Depends if it has pulp or not. Yeah, if it doesn't have pulp, it's homogeneous. If it has pulp, it's heterogeneous. What about blood? Blood is heterogeneous because there's cells in there and plasma, and you can separate the cells from the plasma. If I filter sweet tea, I'm going to end up with sweet tea in the bottom. I'm not going to separate the sugar out. But if I can filter blood, I can filter the cells out. People that do go to give blood plasma. So a solution is a homogeneous mixture that contains small particles. Liquid solutions are transparent, not necessarily colorless. So if you go and get a bottle of Windex in the store, it's that light blue color, you can see through it. It's transparent. That's a solution. Something like Pepto-Bismol, milk of magnesia, you cannot see through, so it's not a solution. Sometimes it's hard to determine. I can't really see through this Coke bottle, so I'm not sure that Coke's a solution. I might need a brighter light. Two parts to a solution. The solute, which is a substance present in the lesser amount, and the solvent, which is a substance in the greater amount. So if I dissolve sugar in water, the sugar is the solute, the water is the solvent. When water is a solvent, we call it an aqueous solution. A colloid is a homogeneous mixture with larger particles, often having an opaque appearance. Colloids don't separate. Suspensions do. So Pepto-Bismol really is a suspension, because if you let it sit long enough, it will settle.
Is Jello another example?
Jello is a colloid. Now, vegetable oil and water. Can you mix them? No? You
can mix them, you want.
You can mix them, yeah, they're not soluble, it's not water soluble.
So they're mixing, they're going to separate, right? Always, right? Now, what about if I add the egg yolk to it? I can take vegetable oil, egg yolk, and water, mix it just right, and I end up with a colloid that won't separate. You ever hear of such a thing? No? You have it in your house, in your refrigerator.
Butter. Egg and vegetable oil.
What?
You said egg and vegetable oil.
Egg yolk, vegetable oil, water,
You said mayonnaise.
mayonnaise. That's how you make mayonnaise.
I thought you were writing.
It's egg white, so.
Egg yolk.
Egg yolk.
Yolk.
That's like,
The yellow part of the egg.
Yeah, I have it. And it's white. I thought it was the, okay. I thought it was always the white of the egg. Okay.
that's what mayonnaise is not cholesterol. The yellow.
I thought it was the white.
Which is why you don't want to leave mayonnaise sit on the outside when you have a picnic, because it will spoil. Okay. We can have different types of solutions. We tend to think of a solution as a liquid. A solution can be gases dissolved in each other. Air is a solution. It can also be a liquid dissolved in a metal. For example, mercury dissolved in silver. Very common solution. Mercury dissolved in silver. Anybody? No. Bet you a lot of them. A lot of you have them.
Fillings?
But fillings, yes, silver fillings have mercury in the silver.
Is that bad for you?
There was a lot of controversy about whether it was bad for you because everybody looks mercury's bad for you. But I mean, people have had them for hundreds of years. Maybe not hundreds.
I think kind of going to more porcelain there because of that.
Well, yeah, porcelain is cheaper to get away from the mercury. A lot of people have had their fillings removed, the old silver fillings, but
Yeah. Aren't they kind of bad when you have to have an MRI if they yank out of your
No.
MRI?
No.
So they do that. No, they do it with pacemakers, letting know if they would affect the.
pacemaker has what kind of case on it?
Oh, yeah, whatever.
Silver's not magnetic, so it's not going to pop out of your
But, you know,
teeth.
that MRI doesn't pull that much out of it. It says it pulls fire extinguishers and stuff. I got a piece of metal on my knee.
Well,
Alright. What's I going with this? You could also have solids dissolved in solids. We call them alloys: brass, bronze, stainless steel. Somewhere with them, I forget. Okay. A substance that conducts an electric current in water is called an electrolyte. A substance that does not conduct an electric current in water is called a non-electrolyte. So if you put an ionic compound in, like sodium chloride, it dissociates into Na plus and Cl minus. So if you have anions, you have transferred electrons. When you transfer electrons, you can conduct electricity. That's what electricity is. Something that doesn't dissociate it, here they have hydrogen peroxide, won't conduct electricity. So if you're standing in distilled water, it doesn't conduct electricity, and it gets hit by lightning, and you're okay. If I throw sugar in the water, sugar doesn't dissociate. You're still okay. If I put a teaspoon of salt in there, your blood is fried. Okay? Because that will conduct electricity. When you hear the term electrolyte, what do you think of? Gatorade, Powerade, Pedialyte. So, a little biology here. Very little, because I'm not a biologist. Okay, we go down. Your nerves. You've heard of calcium channels, sodium channels, potassium channels. At your nerve ends, how do nerves work?
They conduct,
They conduct
electrical
Ions.
signals.
electrical signal.
Action potentials.
So you have to have ions at the ends of the nerves. So you have your sodium and your potassium and calcium, and those conduct electricity. Now, you go out all day, you're running, working in the yard, you work up a good sweat, and you come in, the sweat dries off. What's your shirt look like?
White.
White, because of the salt. Where's the salt come from?
Your sweat, your blood.
And ultimately it came from in your body. So you reduce the amount of salt in your body, so the number of anions and cations. So you reduce the number of electrolytes. So now you don't have the proper number of electrolytes at your nerve endings. What do your nerves do? They kind of short circuit. What else do your nerves control? Muscle movement. So what happens? You cramp up. That's why you see athletes that be out in the field, all of a sudden they'll fall over because their muscles are cramped. So the solution to that is to rehydrate, not just water. You want to have anions, salt. So they used to take salt tablets, drink Gatorade, which is mostly salt, eat a banana. In extreme cases, they'll take you back and put a saline IV in you to get the electrolytes into your solution, into your blood real fast. Solubility. Solubility is the amount of solute that dissolves in a given amount of solvent. Usually reported in grams of solute per 100 milliliters of solution. And we'll get to some solubility calculations later on. A saturated solution contains the maximum number of grams of solute that can dissolve at a specified temperature. So if I have a glass of water and I add a teaspoon of sugar, I can stir it, it'll go in. I can add a second teaspoon, stir it, it'll go in. There'll come a time when I add a teaspoon of sugar, no matter how often I stir it, it won't go into solution. That solution is saturated. It has as much sugar in it that it can hold. An unsaturated solution contains less than the maximum amount that it can hold. So let's say my glass of sugar, I figured I could hold 5 tablespoons of sugar. If I only take a glass of water, put 1 tablespoon of sugar, it dissolves, it's still unsaturated. It can hold more. Basic rule of solubility: like dissolves like. So most ionic and polar covalent compounds dissolve in water, which is polar. Salt dissolves in water, it's ionic. Baking soda dissolves in water, it's ionic. Sugar is polar covalent, it dissolves in water. Ethanol, ethanol can hydrogen bond to water, it dissolves in water. And I'm sure you all know that, or at least most, well, probably most of you know that. Ethanol dissolves in water. Ethanol is drinking alcohol. The alcohol you can drink. So beer, wine, whiskey, vodka.
So it's not rubbing alcohol.
No, it's not rubbing alcohol. You do not want to drink rubbing alcohol.
I don't want to do that. Always fun.
There are all kinds of different alcohols. Ethanol is completely different. If I remove 1 carbon from that, go to 1 carbon, and I have methyl alcohol or methanol, that's wood alcohol. You don't want to drink that, that'll kill you too.
Hey, you make those homemade ice packs where you put up water in the Ziploc bag and you add just a little bit of rubbing alcohol in there.
Yep.
And it makes us conform. That's kind of cool.
Yep. And strange thing, if I take 50 mils of ethanol and add it to 50 mils of water, how much solution will I get? You should know by now if I ask that question, 100 mils is not going to be the answer. I actually get 96 mils. What? Why is it less?
Yep, right.
My God, why is it less? All my math has just went right out the window. All right, well, it turns out the ethanol can hydrogen bond to the water. So normally if you put two molecules together, they just get a certain distance apart. So 50-50 makes 100. But now the hydrogen bond, it's like these molecules are hugging. I'm not going to hug you. But you get pulled closer together, so the actual volume shrinks. It can actually get closer than it normally would.
Yeah. So what you're saying, if I have a liter, 2 liters, 50-50, and when I put in 100, it would be less than 100 in the
Yep.
read.
Yes.
That's crazy. Okay.
Nonpolar compounds are soluble in nonpolar solvents. So octane, which is gasoline, dissolves in carbon tetrachloride, because there you only have London dispersion forces. So you're going to do some painting, and you go out and you buy oil-based paint. You get done, how do you clean the brushes? Gasoline, mineral spirits, some nonpolar compound. You paint and you use latex paint. How do you clean the brushes? Water. This is why if you're going to paint, let's say especially kitchen cabinets that have been painted, a lot of the old-time paint, they use oil-based paint because it's very durable. It's extremely durable. So you'll have oil-based paint on your kitchen cabinets, then you go and you put some nice latex paint, you paint over the top of it, and it looks real nice until you touch it, and it just peels right off because you've got oil-based paint and water-based paint, and we know oil and water don't mix unless you have egg yolk. And actually use egg yolk in paint.
Really?
It's Tempura paint or something. Old artists used to use it. So. Okay. Now, when you dissolve something, it's called solvation. When you dissolve something, if it releases more energy, it's required to separate the particles. Because remember, when you add the particle, you got to pull it apart. In a lot of cases. The overall process is exothermic. Heat is released. A good example of that is sodium hydroxide in water. Sodium hydroxide is lye, either Drano, Red Devil lye. You used to be able to get it in the crystal form. I don't think you can get it in the crystal form anymore. If you add it to water, it will heat up. So if you had a clog in your pipe, pour a couple teaspoons of Drano crystals down there, and you'd add water. It was always cold water, never hot water. If you add hot water, the reaction heats up. It would get so hot it would cause the water to boil. And usually what happens, people pour it down there and pour hot water in and go, I wonder if it's working. Stick your head over the sink, and the water would come shooting out, and hot sodium hydroxide, hot lye solution will melt your face off. Okay? They use, so liquid Drano, I'll get it on you.
What's not the same stuff as basically in your stomach, is it?
As what?
What's the stuff in your stomach?
Hydrochloric acid.
Yeah. those
No,
are
it's completely opposite. Bases do a really nasty job on skin and fat. My father-in-law worked at the air conditioning company. That's what they use, sodium hydroxide solution to clean the condenser coils. He was filling up his tank in his truck, the main tank. The hose slipped out and went down his back. His boss, not knowing any chemistry, said, go on home and change. So he's driving home and felt tingling. By the time he got home and in the shower, he had third-degree chemical burns all down his back and leg, and was in Chapel Hill Burn Center for several weeks getting skin grafts. So, sodium hydroxide, because it's for animals, reacts with animal fat to make lye, and animal fat makes lye soap. So you get it on you, you're essentially making soap out of yourself. And it will dissolve. So Lime is another thing that'll do it. So farmers, cow dies in the field, they take a bulldozer, dig a big hole, throw the cow in there, cover it with lime, cover it back up. The lime eats the fur, the skin, everything down to the bone. Go fast, so it prevents
You said lime?
lime.
Lye.
Well, you could do lye or you could do lime. Lime is cheaper. There was a case in Ireland a number of years ago. I don't know if that picture's in your book, where a father had two boys and the wife left him, and he was kind of a drunk and that. So one day, the boys disappeared, and he said they went to live with his mother. Well, several years later, they found out that he killed them and stuck them in a peat bog. A peat bog is very basic, like lye. So essentially, they found the kids, but the kids were completely turned to soap. I don't know if that picture's in your book, but it's... So, the other part, if the separation of particles requires more energy than is released during solvation, the process is endothermic. That's the basic behind those chemical ice packs. You break that little bag inside, and when you shake it, it forms a solution with the material inside. It's endothermic, so it needs heat. Where does it get the heat from? From your hand, from your body, wherever you put it on, so it feels cold. It absorbs the heat from your body. Temperature effects. For most ionic and molecular solids, solubility generally increases as temperature increases. So, you want to make rock candy. It's very simple. 3 cups of sugar, 1 cup of water. If you take 1 cup of water and dump in 3 cups of sugar, you'll be stirring it until the cows come home. It won't go into solution. You have to heat it. The way to do it is take the water, heat it on the stove in the pot, add the sugar slowly. It will go in. You will get the sugar in, it'll get real thick, almost like a syrup. You get it right till it just starts to boil. Careful, because it'll splatter. Take it off and carefully pour it into a glass or jar. Take a string, wrap it around a pencil, put a little weight on the bottom of the string, hang it in the jar, and let it cool slowly. As the temperature goes down, the solubility of the sugar goes down, so it starts coming out of solution as crystals. It will crystallize on the string. Slower it cools, the bigger the crystals. When you're done, it's rock candy. Rock candy are just sugar crystals. If you want it flavored, you can go to the cooking aisle in your grocery store and get whatever flavoring you want, root beer, orange, cherry. Put it in there and it'll taste like that. If you ever buy rock candy in the store, you usually see it on a string. That's because they hang the string in there. Or sometimes on a stick. If you're very careful with some compounds, you can heat up the solvent, dissolve more and more solute in it, and then cool it very slowly, and it won't come out of solution. You end up with what's called a supersaturated solution. That's the basis behind reusable hand warmers. You get this hand warmer, and it'll feel real liquidy. And inside there's usually like a little metal disc, and you grab the disc and you flex it a little bit, and it starts crystallizing. And the stuff that was, the excess stuff that was in solution starts coming out as crystals. When it comes out, it releases the heat that you used to put it into solution. So it gets hard, and it gets warm. And it'll keep your hands warm for a couple hours.
Yeah, I have a canvas bag like that. It has like some chips or something that, and you pour a teaspoon of water in the pouch, and you massage it, it gets real hot.
That's a different thing. But the reusable ones, then after it stops, you can take it home and you just stick it in boiling water, go back in the solution, and you just let it cool real slowly. And a lot of it's very stable. You can carry it around. If you hit it just right, it'll crystallize again.
I didn't know you could reuse those. They're like fuel warmers for the baby chambers.
do the little flash thing, but you can actually see it, just like you see it crystal through.
Yeah, stick it in boiling water. Do not stick it in the microwave. Because it's got a little metal piece in there.
Oh, yeah.
Yeah, you don't want to stick metal in the microwave. So just stick it in a pot of boiling water.
Oh,
Gases, on the other hand, decrease with increasing temperature. So your sodas, your Cokes, and your Mountain Dews, and whatever you guys are drinking, they bottle it under cold temperatures, so they can get more gas into the solution, more CO2. So, summertime, end of July, August, a lot of times you'll see on the news, there'll be a creek or a river or part of a lake, and you'll see hundreds of dead fish. Why? Yeah, when it's hot, what happens when it gets hot?
The surface gets really hot, but the bottom is still really cold.
It'll rise and it messes with the oxygen levels.
Well, what did I just say? Gas is more soluble at what? Cold temperature. So when it gets hot, what happens to the oxygen dissolved in the water?
Oh, there's not as much oxygen.
Yeah, it leaves. It comes out. The oxygen comes out. So the oxygen comes out. What happens to the fish? They die. They suffocate. Yes. So if they're in shallow parts of the lake or that, like you said, deep part of the lake stays cold. They can't get to that deep part. There's a big heat wave, and that they just belly up.
It happens every year in Wisconsin.
Gets hot in Wisconsin?
Well, yeah, a couple days a year.
I was gonna say. Days or hours?
Huh?
Days or hours? Okay. Pressure effects. Henry's law, the solubility of gas in a liquid is proportional to the partial pressure of the gas above the liquid. So basically what it's saying is the higher the solubility, the higher the pressure, the higher the solubility. So again, your Coke, your carbonated drinks are bottled under high pressure. If you try to make your own soda by taking a glass, putting in water, flavoring, and sugar, and throwing in dry ice, which is CO2, and let it bubble, well, now you got CO2. And if you taste it, it tastes like crap because you don't have enough CO2 in there. So CO2 has to be put in under pressure. So if you're at a fast food restaurant, you go to get a drink and it's flat, you tell the guy it comes out with a big container of CO2. Or the one they got for home now, SodaStream. It uses little cartridges of pressurized CO2 so it can put the CO2 in under pressure. So now, it's put in under cold temperature, high pressure. Shipped to your grocery store, the temperature goes up. What happens to the gas in the solution?
Goes down.
Well, the gas in the solution goes down, so it comes out, but it's trapped inside the bottle. So what happens to the pressure inside the bottle? It gets really tight, so the bottle's really hard. So now you go home and you unscrew it. So you release the pressure. So now the pressure above the gas goes down, above the soda goes down. What happens to the solubility of the gas? As the pressure goes down, the solubility goes down. So the gas comes out of solution. So what happens when you open the bottle?
Releases.
Releases what? Bubbles.
Yeah.
That's right. That's what makes the soda bubble.
Also, then it gets flat.
Well, after a while, so now, let's say that one, she's opening it, she sees she doesn't drink it, she put the top back on. Some of the gas is going to come out, and it'll still be fairly hard. And she'll do it again, or some going to go, psst. Okay, and it'll come out. Well, after a while, it'll go flat because there's no more gas to come out. So if you want to keep it, if she took that bottle, put it in the refrigerator, it'd probably be good later this afternoon. If you just let it sit out on the table, chances are it'll be flat. Higher temperature, the gas keeps coming out.
Is that why they have like the pumps for the 2 liters?
Yes, that's why they have the pumps for the 2 liters.
Oh. So, it's the
That's what
gas.
we just talked about.
You put the pump in there that increases the pressure inside that keeps the gas from coming out.
Could
Keep
do that
it-
with wine.
You can do that with, well, wine's not carbonated.
You can do something with
Wine, you want to actually get rid of the air above it because that starts oxidation process, and that turns the alcohol into acetaldehyde and essentially acetic acid, and eventually wine, if like the cork leaks or something, you got good wine, or screw top leaks. You'll have vinegar after a while. Now, there is a process where they take wine, because fermentation, usually when you make wine, you start a fermentation process, you make alcohol. When the alcohol gets to the certain level that you want for the wine, you stop the fermentation process. Now, in some cases, you don't stop the fermentation. You bottle it while still fermenting, and you stick the cork in it. Fermentation releases CO2. So if you don't stop the fermentation, what are you going to be making?
It's champagne.
CO2. So the CO2 builds up in the bottle. When you pop the cork, that's how you make champagne. Also, you may have seen this phenomenon if you were young. Sometimes you have these little toy rockets, plastic ones that you fill up with water, and you put on this little pump thing and you pump it up, and you push the thing and release it, and it goes shooting up in the air. That's because when you press on it, you've increased the pressure, you put the air, and when you release it, it pushes the liquid out, which then shoots the rocket up. All right, here comes the math. Concentration. Weight, volume, percent concentration. So the concentration of a solution tells how much solute is dissolved in a given amount of solution. So the higher the concentration, the more solute is in there. So 10% alcohol versus 50% alcohol. 50% alcohol's got a lot more alcohol in it. So to do, and it's, you may see it either as weight/volume or mass/volume, M/V. Percent is the mass of the solute in grams divided by the volume of solution in milliliters times 100%. It's a percentage, like any other percentage. The part over the whole times 100. So if I have 100 mils of solution with 5 grams of sugar, what's the percentage?
You said 100.
5 grams of sugar per 100 mils of solution. What's the percentage? You guys got to, oh boy.
I have a clue.
So if I say 5 grams of sugar over 100 milliliters times 100, what's the percentage? 5. I chose 100 so the hundreds would cancel. So if I had 5 grams of sugar in 50 milliliters, what would my percentage be? Quick. What? Yeah. 5 grams of sugar in 50 milliliters.
1%.
10%.
10%.
5 grams of sugar in 50 milliliters times 100. 50 goes into 100 how many times? 2 times. 2 times 5 is 10%. Five grams of sugar in 10 milliliters? 50%. Thank you.
I see the equation in my head, I just see it.
I don't know, you guys can go into a store and shop for shoes and purses or whatever, and you guys can rattle off those percentages like crazy. And you go in, oh, that Coach purse was $300, it's 10% off, how much is it?
$3 off.
Yeah. See, you just did that in your head.
I can tell you that.
Same problem. I don't understand. So here, vinegar, 5 grams of acetic acid and 100 mils of solution. So what's this percentage? 5. I mean, you got to read the screen. It's 5%. So pure acetic acid will take the skin right off of you. But 5% we eat with French fries or whatever we put vinegar on. Huh? You ever had French fries with malt vinegar? Oh, that's great.
That's a thing in Dutch. That's how they fry for Dutch.
Yeah.
That's how they ate them in England when I was.
Yeah, in England. A lot of the European countries eat it. Oh, that's so good. Malt vinegar,
Like fish,
fish and chips, yeah.
Oh my God.
Oh, you gotta try that. Fish and chips. It's fried fish and French fries. In England, that's what chips are. They're French fries. They're fried potatoes.
Salt and vinegar potatoes. The same concept, salt and vinegar potatoes.
Okay, they use mass volume concentrations when they're usually going to dissolve a solid in a liquid. So if I'm going to make a 5% saline solution, and I'm going to make 1,000 mils of 5% saline solution, how many grams of salt do I need? Let me go back one here. So I want 1,000 ml of 5% sodium chloride solution. How many grams of sodium chloride do I need? Well, let's look. I want 5%, right? I don't know how many grams. This is 1,000. X is equal to 5 times 1,000 divided by 100. X is equal to you guys need a calculator to do that? 100 goes into 1,000 how many times?
10.
10. 10 times 5 is? Thank you. 50 grams. All right. I urge you to learn how to do that. There was a case recently where a nurse had to give a saline solution, and it has to be a certain percentage to the patient. Did this calculation, she didn't want to use a prepared solution, missed it by a factor of 10, killed the patient. Not good.
In that situation, she would have to take the patient's weight into consideration too, right?
Don't have to take the weight into consideration, no. It is certain when we get to isotonic solutions, it's the same no matter what weight you are.
Isotonic and then there's isometric or?
Isometric's an exercise. Isotonic, hypertonic, hypotonic. Yeah. What if you could dissolve a liquid in a liquid? Volume percent. It's the same formula, except you have the volume of the solute in milliliters, the volume of the solution in milliliters. So, here's your bottle of rubbing alcohol. Contains 70 mils 2-propanol in 100 mils of solution. What's its percentage? 70%. Pardon? All right. So you can buy isopropyl or rubbing alcohol in the grocery store. You can get 50%. You can get 70%. So, and if you're looking at alcohol, in terms of drinking alcohol, the proof is twice the concentration. So if it's 100 proof, it's 50% alcohol. If it's 190 proof, it's 95% alcohol. So above a certain level of alcohol, it will actually burn. That's why they go to those bars and they have those weird drinks that they set on fire.
40%
Oh yeah?
That's what,
Well, you put in 140 proof alcohol, it doesn't really matter what you put in with it.
it just makes you have to have.
If you drink enough of it, you may still cough, but you won't care. Okay? So, NyQuil, DayQuil, that's all like 20 proof, it's 10% alcohol.
Oh, yes.
Oh yeah.
So you make it off something.
What'd you say about NyQuil again?
It's 10% alcohol. Unless you get the one that's specifically without alcohol in it. Most of them have 10% alcohol. And if you take it, you don't use that little cap that comes with it. Just take the bottle, half a bottle of that, you'll sleep through the night. Okay.
You won't like die?
What?
You won't die.
You won't die?
I thought if you drink more than you're supposed to, you die. No. I drank a half a bottle of it.
No, not necessarily.
It'll make you sick to your stomach, do all the syrup.
Well, you'd have to drink probably 20 bottles. I mean, 10% alcohol is 20 proof. 20 proof is maybe what a good wine is. So if you drank a glass of wine, it'd be like drinking a glass of wine.
You can save the money. You can save the money on the open.
This is why they have a lot of underage kids go out and buy that. It's got alcohol in it. It just doesn't taste like wine.
I mean, it's probably got Tylenol in it too, I'm pretty sure, so you could
Yeah.
kind of overdo it all the time.
Maybe it's Tylenol in that, but even that, there's a big, over-the-counter medicines, there's a big safety margin. You've got to really go out of your way. All right. Here we talked about the saline solution. The one that you need to give people is 0.92% weight volume in water. How many grams of NaCl are contained in 250 mils of this solution? So, let's look at this. Remember, percent weight volume is grams of solute, in this case would be NaCl, over milliliters of solution. Well, how many milliliters do we have? 250 times 100. What was the percent? 0.92 grams over 250 times 100. So to figure out how many grams you need, 0.92 times 250 divided by 100. 2.3. That's the person who's looking ahead in the slides. Oh, you did it in the calculator.
Yeah.
Did it in the calculator, okay. Usually when people say that fast, they just like, oh yeah, they got the PowerPoints in front of them. Okay. So that's all there is to it. 2.3. lot of times when the solution contains a very small concentration of solute, we express it in terms of parts per million. Parts per million. It's the same formulas, except that instead of multiplying it by 100, we multiply it by 1,000,000. That's used a lot when we have very small quantities. Usually if you have a well and you send the water out for analysis, they'll come back and say you have so many parts per million arsenic and so many parts per million chlorine. So very small amounts.
Why do we need arsenic in the water? Why do they put it in water?
They don't put it,
Are you serious?
it just comes from the minerals. They don't add arsenic. But remember, arsenic is contained in your body. It's one of those trace minerals.
Is it poisonous? Is it really poisonous?
Yeah, it's right poison.
Yeah. In larger enough quantities. There was a woman where I worked that poisoned her husband with arsenic.
Really?
Yes.
Why?
She didn't like him. She was having an affair and she wanted to get rid of him. The thing about arsenic poison is cumulative, so she actually had arsenic compounds where she worked. Not smart using that because they can trace stuff back. But she gave it to him, he got sick, he went to the hospital. He got better, he was in the hospital, he came home, gave it to him some more. He got sick, went to the hospital. And this time she went and visited in the hospital and brought him food. Guess what was in the food? Arsenic.
She loved them.
Did he die?
Yes. He died. Her lover killed himself.
Didn't she do her, well, I'm going to talk about it instead of seeing on some of her kids, so she started doing it.
No, this isn't the one. And then she moved to Wilmington. They tracked her down. It's hard to prove. Hard? She worked where I worked, yeah.
Is she in prison now?
I think she might be in prison. It was hard to prove that she... Huh?
You knew her.
Well, I knew of she worked where I worked. Which is fun because we have arsenic compounds there, so that's where she got the arsenic from. We traced it back. She had arsenic in her lab. Arsenic compounds.
Why didn't she just divorce her? She was
Who's all the money? Who's all that money?
Good question. I don't
She
know.
was crazy.
And that's how they got rid of Napoleon, too, by the way, was arsenic.
Oh.
Arsenic, actually, if you take it, accumulates in your hair, so that's how they found out they got him. Many decades later, they dug up his body, cut a sample of his hair, and analyzed the arsenic in it.
Oh my goodness.
So they figured out they poisoned.
Can you build a nuance up to it?
No, accumulates, and then after a while, he just died.
Because Hitler did some stuff like that. He'd take all kinds of poison to keep his.
He did different.
He did different kind of poison, so he ingested every day to keep his minions from poisoning him.
He did like
freaking them.
nitrous gas.
New concentration unit. Percentages, and that's what you see in the grocery store. Now we're going to use the chemistry concentration unit called molarity. Molarity is defined as the moles of solute, so here's where the moles come back. What would you do? Come back. Per liter of solution. So the higher the molarity, the more concentration created the solution is. So calculate the molarity of a solution made from 20 grams of NaOH and 250 milliliters of solution. Uh-oh. We know molarity, which is a capital M. It's moles of solute, in this case it would be moles of NaOH, per liters of solution. How many liters of solution do we have? How many liters of solution? Pardon? I didn't hear you.
250.
Nope. That's 250 milliliters. How many liters?
Okay.
20.
Liters to milliliters. You gotta convert liters to.
Yeah, milliliters to liters.
Milliliters to liters.
How many milliliters in a liter? So to go from milliliters to liters, to go from 1,000 to 1, what do I have to do? Divide by 1,000. So 250 divided by 1,000 is 0.25 liters. All right. I need moles of NaOH. Do I have moles of NaOH? No, I don't. I have grams of NaOH. What do I have to do? I'm sorry, what? Oh, yeah, I got to convert it to moles. Yes, exactly. Uh-oh, back to the stoichiometry roadmap that you all love so much. Yes.
Is it grams the whole time?
Yes, grams of A to moles of A. So 20.0 grams. 1 mole of NaOH weighs how many grams? Well, sodium is 23, oxygen is 16, hydrogen is 1, 40. So how many moles do I have? Don't use the calculator.
20, you do 20 divided into 40.
No, they convert moles and grams.
I just did that time. How many moles?
You cancel out the grams.
25, thank you. Somebody said that earlier. 20 divided by 40.
20 divided by 40, yeah.
0.5 moles. So now, I know I have 0.5. Without using your calculator, what's 0.5 divided by 0.25? Thank you. Huh? 0.50 divided by 0.25. What's 50 divided by 25? 2.
It's right there.
Slow down.
Be over 25, right there.
Slow down. You must be a riot to watch balance your checkbook. I mean, it's like just all the numbers. Okay, take your time. Take a breath. Look at the problem. Two. Okay. Well, what? What'd you ask? Why is it?
Yeah. That's different than what you had.
What I did?
No, it's same thing.
What was it saying?
I just didn't put the number of significant figures in there.
Oh, okay.
Is it hot in here? Or is it just
Yes.
me?
It's really hard.
It's really warm in here. I thought it was.
We should get
Did you get what? What was that?
turn the arrow.
That's not what she said. She said you should get out early. I told you. She did. Okay. Wow. Did you even see that bus coming? She just threw you right under there, didn't she? She didn't care. She said, I don't know. You should get out. Who said that? She did. All right. Okay. I tend to agree with her. But you want to stay, so okay, we'll stay. So, molarity is a conversion factor. In other words, we can rearrange that equation. That's all that's saying. So molarity is moles over liters. So we could say moles is molarity times the volume in liters. The volume in liters is equal to the moles divided by the molarity. The same way we rearrange the density equation. Okay? So, given 2 out of the 3, you should be able to solve for the third. That's all that is saying. Question? So, here's a problem. One volume in milliliters of a 0.30 molar solution of glucose contains 0.025 moles of glucose. All right. What's the molarity? How many moles of glucose do we have? I want to know. First of all, I can solve for liters because molarity is moles per liter. So X liters is 0.025 moles divided by 0.30 molar. So liters is what?
Divided by 0.025.
0.025 divided by 0.3.
That was the second point, so.
Say again.
0.025 divided by 0.3.
0.08.
0.083?
0.083.
Okay. So 0.083 what?
No, it's 0.083.
That's what I just said.
Okay.
Liters, right? And what did the question ask for? The volume in?
Milliliters.
How many milliliters?
Oh, so it's be put it over to,
Hey, this was the letter you
What?
833.
No.
830. Oh, 83, that's right. Hannah got it, she said 83.
83. 0.083 times 1,000?
I was trying to just look at this one.
Yeah. 1, 2, 3. 83 milliliters. So the answer is 0.083 liters of solution, 83 milliliters. Okay. So 83 milliliters. So we can use the molarity equation to actually calculate grams of solute. Because the molarity gives us the number of moles per liter. From the number of moles, we can get the number of grams. Moles of solute, grams of solute, you multiply by the molar mass. Stoichiometry roadmap. Moles of A to grams of A is going in the opposite direction. So you multiply by the molar mass. Solutions. It's the addition of solvent to decrease the concentration of solute. The volume changes, but the amount of solute is constant. So a lot of times you buy stuff in the grocery store, it's concentrated, so they want you to dilute it. They don't want you to use it concentrated. You go to Home Depot and you're going to buy pesticides, sometimes it's concentrated, you have to dilute it with water to get the right concentration. If you want to kill the bugs, you don't want to kill all the people and animals. Well, maybe you do, but... The equation is very simple. M1 V1 is equal to M2 V2. Where M1 is the initial concentration. V1 is the initial volume. M2 is the final concentration. V2 is the final volume. So, without even looking, just think about this conceptually. I have 1 gallon, I'm going to use English units now, so I don't confuse you, 1 gallon of a 10% solution. I want to make a 5% solution. How much water do I need?
Another gallon.
Another gallon.
Oh,
2-to-1 ratio?
Yeah. So you guys did that in your head. That's all that is. So if I had the concentration, it doesn't have to be molarity. I said I had, what did I say, 10%? It was a 10% solution. And I had 1 gallon. I want a 5% solution. What's my final volume got to be? So V2 has got to be equal 10% divided times 1 gallon divided by 5%. My final volume, 2. What happened to my pen broke. Two gallons. You all did that in your head. So if I give you any 3 out of these 4, you should be able to solve for the 4th. You just did it. That's as hard as it gets. The only thing, and you knew there was something coming, you have to be careful of, no, your volumes on both sides have to be in the same units. And your concentrations have to be in the same units. So, how many milliliters of a 4% solution must be used to prepare 250 milliliters of a 0.08% solution? All right. What's the initial concentration? 4%. How much of it do I have? Nope. What's the question asking?
Oh, you have 0.0.
No, but what is the question asking? How many milliliters of that do I need? So do I know? No. So we don't know V1. What is the final concentration that I want to end up with?
250.
No, that's not a concentration. What is the final concentration?
0.080.
How much of it?
250.
250 milliliters. So V1 is equal to 0.080% times 250 divided by 4.0%. V1 is equal to what? 5. 5 milliliters. All right? You're not okay. You probably have done that in your head.
No,
I know you usually calculate. Really? 4 goes into 8. twice, so 0.02 times 250, 2 times 250 is
500.
500, move the decimal place over to 5. Sorry, I just grew up in a generation where we didn't have calculators, so we had to learn how to do it with it. So. Is that for me? Questions? You all set on that? All right. 5. How much of this we got left here? Let me stop this for a minute. Pause it.